There we go. Go away. And if you haven't already, I will give you 2-ish minutes to get through this. If you can get through this, you should be fine on the quiz. If anyone needs paper, let me know. I have some. I'll give you a couple pieces of this notes.
Did you have a spare pencil for today?
Yes. I know I'm going to have a lot of things to type, all that stuff.
A pen file.
Yeah, I got pens. Paper?
Just put.
This one is easier to talk in. Oh my god, why is that so clear? All right, another couple seconds, and then we'll talk about it, and then we're going to move on to our next section. Section 1.2. But I want to talk about it. I have paper copies. And if you don't want a paper copy that I've touched, you can also use it. Yeah. But very nice. It's the last 15 minutes, so we end at 2:30, so I might stop talking. Alright, so let's start going over this. So if I wanted to complete the truth table for this guy right here. Whoa, what have I done? No, I haven't. Here we go. So, of course, we want to start off in Q. Column true, false, 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 true, false. I'm going to do it this way because I want you to do it this way on the quiz. I know technically if you're considering not something, you can just technically look to see where it's false, but I'm going to want you any not column not in there anywhere. I want you to make sure that column makes it into your truth table. False, false, true, true. And the thing I would personally do, well, only can do is the Q and not P column and the not P to be true. So true, false, 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 true, 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 false. And then finally I can do the implication. Feel free to chat if you have a question. There's already a bubble. Oh, it's just the fact that I started recording. Okay, cool. Because this setup is a little wonky today, people on Teams, it might take me, it might take me a bit longer to realize that you've sent me a chat, but I will try to remember to check that every once in a while. Okay, so now we can application. So we want to check isn't working. Can y'all hear me? I'm gonna wait like 5 minutes.
It's going in and out.
Yes.
Hopefully a very simple plug out, plug back in will help. I'm gonna start babbling for a little bit. Tell me if it's going in and out. I'm just gonna keep saying words for a little bit, for about a couple more seconds of just saying random words, and not making any sense. Was that any better?
Yes, it is.
Hooray! Okay. Okay, what was I doing? Implication. So true implies false is the only case where the implication is false. So we have false. True implies false again is false. False implies true is true, and false implies false. True. It's telling me it's not working again. Has it gone in and out again?
I hear it fine on my end, but I guess on everybody else's end is different.
It's fine? Okay, so I'm going to assume it's fine and that Teams is lying to me. If it ever starts going back in and out again, just, chat me. Okay, cool. Questions on the tree tip? Oh, it's going first. Savvy. All right, I want to make this go away. Ugh, these multiple setups is just a pain in the butt. There we go. Okay, so given that, I know these are a bit silly, but given that P means you are purple, Q is it is raining, and R is the cat is sad, what would P and not Q implies R mean in English? Well, if I just start writing down what these mean as I go, I have P and not Q, so you are purple and not, so it is not. And then, so this is my if. I always do this. It's an implication, so it should be you are purple and it is not raining. And the cat is sad. Sad. And then how would you write the following in symbols? If the cat is not sad or you are purple, then it is not raining. So we do have an if then, so there's going to be an implication somewhere. But the first thing we hit is the cat is not sad, so that's going to be not R. So not R. Or purple, which is our P statement. So not R or P. And that's all before the then. So that was all in the if statement, if you will. So that's going to be kind of put together. And then it says, then it is raining. So implies. Savvy? Cool. Now, last time on Tuesday, we were talking about, we did those really long, obnoxious examples with the tons of words, and you had to transfer them into symbols and do a giant, obnoxious truth table. And there was some questions about, well, how do you know what to group when and where and why? And I did some digging, and the answer came out to be exactly what I thought it was, which is it just takes practice. So there is technically, in general, a precedence for symbols. The reason I'm not going to tell you what it is, you can Google it if you want. You just literally Google logical connectives precedence. The reason I'm not going to present it to you, because I don't want to confuse anybody, is because once we start getting into English examples, the examples where they're all just stated in English, those kind of go out the window and no longer work. Okay, so if I were to do the one of the last questions we did last time with those precedence rules in mind, I would actually get it wrong, because in the context of the English language, it kind of tells you where they should go, and it just takes practice. And I know that's an unfortunate thing. Like, I really wish I could just throw a couple tips and tricks at your face. But as I originally feared, I can't. One thing I will say, though, so let me go back. Oh, you can't see what I'm doing, because, right, I got to unshare my screen, and then I've got to, let me just share my desktop for Pete's sake. I just want to talk about the one example really quick to try to go over how you could possibly see in the context where it was going from. So this Aaron one, so the last one, I think it makes a bit more sense because there's kind of less going on. But up in this one, and I got to move that. Or I can't. Okay, let me just zoom in then. So kind of the context that's going on that can help you figure out how this was supposed to go is, so you have, if Aaron is late, then Bill is late. So that's already a completely, nope, I'm already going the wrong way. So if Aaron is late, then Bill is late, but then right after the and is another if. So you kind of know that that implication that was already there is now done and completely isolated, okay? So if it had said something like, Aaron is late, then Bill is late, and I can't write on this, crap, and class is boring, then the Bill is late and class is boring would have went together in that and been the end of the implication. But since after the and it went into a new implication, you kind of know that that breaks it up into those two pieces. And then for the second implication, if both Aaron and Bill are late, then, well, that and statement is between the if and then, so that must have been paired together as well. So it's kind of like you gotta, it just takes some practice of reading the context and trying to figure out in the English where it's trying to tell you to quote unquote stop each piece. So that's unfortunate. If you want to know the precedent rules for the general strings, you can just Google it, but I don't want to present it in case it confuses anybody, because when English comes into play, it goes out the window. One other thing I wanted to say specifically about your homework. So again, your homework's already up. Hopefully you've already kind of been looking at it. I always suggest kind of chipping at it throughout the week. You can't necessarily do it right away because we don't cover everything at the very beginning. It covers stuff that we cover throughout the week. But one thing I wanted to talk about, do it. Thank you. And I was messing around with this yesterday and I was just clicking answer, so I wasn't trying to get it right. But whenever you're looking at a truth table example, and I kind of mentioned this, but I wasn't sure it worked that way, so now I know it works that way, so I want to double check that everyone gets this. So you only have one chance for each of these, for each and every single one of them. You have one chance because there's only two options, so you only get one chance. So to make sure you don't do the entire thing and get the entire thing wrong because you messed up one piece, I would suggest filling out one column, hit submit answer. Wait for it. Oh, now okay, thank you, bring me back. I got it all wrong because I wasn't actually paying attention. Oh, that was not P, that would have been easy enough. But anyway, so now I know all of those must have been the other thing that I didn't put in, and now I can hopefully complete the rest of it correctly. So you can kind of like go halfway and check your answer along the way. You don't have to do it all in one shot. Just so that that's clear. I think that's all I wanted to ramble about before we got to notes. Yeah. So notes. Where are my notes? No? Where are my notes? Oh, they're here. There we go. So again, to try to minimize the amount of stuff I'm handing to you guys, I'm not going to be printing these out for you anymore. But again, always these blank ones are on Blackboard. They're up before the class that's going to use them. Like, I don't even think we're going to get to 1-3 today, but those are already up just in case we got there. And of course, all the filled out ones go on Blackboard. So you can either just sit back and listen to me ramble. You can try to take down the most important bit, whatever floats your boat. So we're on to propositional logic. So the last example that I was just talking about is Bill is late, hoopla, hoopla. If you think about that, that had 3 statements, so we called them. So it resulted in 8 rows on the truth table. So I think someone had actually asked me about this. So for every extra statement we add on, it's going to double the amount of rows you have in the truth table. So say 4 statements, it would be 16 rows. And so obviously that's going to start getting very obnoxious very fast. We want to be able to develop something that's going to allow us to kind of prove statements that have more things in them without having obnoxious truth tables every time. And logic is going to help us do. So definitions first. Hey, got to turn on the drawing. Boink. So a tautology. A tautology is a statement that is always true. So say we want to complete this truth table here. Now also I was talking to the other professor who teaches this class who has taught it multiple times as opposed to me. And he suggests tables in also a different format. So I'm actually going to do this one in that format to just show you that it exists. Specifically, people are probably computer people doing other computer classes in their life. Instead of true and false, we can also do zeros and ones. So we'll use 0 for false, true. Works the same exact way. It's now just zeros and ones instead of Fs. If you want to do that instead of T's and F's, maybe because your handwriting stinks between a T and an F, especially, that'd be great. I'm going to do it in zeros and ones for this table, but again, all of the rules still work the same way. So P implies Q, true implies true. So 1, false, true, and P and Q use this and that. So the first true, you have a false, 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 false. And then our last is P and P. So the column we just did. So true false is false is true is, and just to so if we were in the T, so that's an example of a tautology. The very last thing, the thing we actually cared about, turned out to be true in every single situation. So that's an example of a tautology. Now that is actually a proof table for a rule that we're going to talk about in a second called modus ponens. I never remember if I say those correctly, but I think it is modus. I think it's modus ponens. Anyway, so notice that arrow, then just an arrow with a singular thing, and that's gonna using them interchangeably. So if we use this kind of, call it a bold arrow, lack of knowing what else to call it. So that bold arrow is going to be used to represent when we have a tautology, specifically for implications, because we don't have a. So for instance, if we have A, arrow B, mean that the implication A implies B is always true. Similarly, if you do the bold double arrow, if you will, that's just going to mean that the if and only if case is always true. So again, be very careful to not use them interchangeably. Types of arrows, one of them implies it's a tautology, the other one doesn't. I always forget draw to be able to scroll, which is the dumb. There we go. Look how much nicer that looks. Oh, okay. All right. So also new notation. So say we had a statement that was of the form C and D, bold arrow, E. It also can be rewritten like this. Okay. And for the rules that we're about to look at in just a second, they're mostly going to be written in this way. Okay. Now what this is saying is essentially if we know C and D, we can conclude E. Essentially, we have those two things, we can conclude the other one. And since this is implied to be a tautology, essentially just know that having those two things can always get us that third. So,
I'm not hearing you.
sorry, I wasn't checking the chat. That's well, it's probably, a mask.
Hello?
Can you hear me now? Brad,
I hear something now.
you hear something or you hear me?
Okay, I hear you now.
Okay, well, Hopefully my laptop mic will be enough. So some of you said, what did you say? Lord, I missed everything you did with the table. Well, that's a lot. So let's go back there. Yeah, sorry guys. Doing these in 2 different forms is a hoot and a half. So this was just a truth, and I'm not drawing, Lord Almighty. So what I was doing with this truth table, now don't freak out with the zeros and ones if you didn't hear me explain that. All that is that I was reminded that I should probably show you that truth tables can go in a different form. So instead of true and false, especially sometimes people who work with computers are going to use zeros and ones instead of T's and F's. So we're going to let 1 be truth and 0 be false. So I just kind of redid this truth table with zeros and ones instead of trues and false. And at the very end, I came out to all of them being true. And all of them being true means that I'm a tautology. So this was an example of a tautology. So the point of that, so this new notation right here is going to mean that we have a tautology. So if you have A and then this little bold arrow B, that's going to mean that the implication A implies B is always true. And similarly with the if and only if case, it's going to mean that that biconditional is always true. And then say we have a statement that looks like this, C and D, bold arrow E. That's going to be able to be rewritten in this way below. And that's how all of the rules we're going to look at in a second are going to go. So this essentially means if we have C and D, so even though it doesn't have the and symbol anymore, that's what this form is essentially telling us. If we have C and D, we can conclude E, okay? So that's kind of what's going to happen there. Does that make sense? I know that was semi-fast, but the truth table is just a truth table just with zeros and ones, and then new notation. Savvy Teams people? I'm going to assume anyone tell me that they're not savvy. That was bad English. I'm going to assume since no one's telling me terrible things that we're good. Maybe I should just leave that chat up. I'm just going to leave it up. Okay, so we have our new notation. Oh, look, I'm not even touching anything. Stop it. Where am I? Lord Almighty. Okay, so we defined a tautology, and kind of similarly, but the opposite, is we can have what's called a contradiction. So a contradiction is a statement that's always false. I'm going to go ahead and do this in zeros and ones again. So say I wanted to complete the truth table for this thing that you can read. I'm not going to read out loud. I got to remember not to get too far from here. So P implies Q, so true implies true is true. True implies false is the only case where it's false. The other two are true. I'm starting to go through these truth tables pretty fast because hopefully you're getting used to them. If you ever want me to slow down and explain a column again or in better detail, just let me know. Just stop me. So now we have not that column we just did. So false, true, false, false. And then we have Q and the column we just found. So they both need to be true. So true, false would be false. False, true would be false. True, false would be false. False, false would be false. So since we come out, and again, if we were doing this in letters, these would all result in false. So this is an example of a contradiction. It came out false in all situations. And so we have names for, always true and always false, but there are lots of things that are not always true and not always false. But we also have a name for that too. So a contingency is a statement that is sometimes true and sometimes false. So, wow. So tautology, contradiction, contingency. So now, let's get into some rules. So tautologies are important because they're essentially going to allow us to derive new statements that are essentially going to be equivalent. We're going to be essentially using these things to replace, and that's how we're going to be using our proofs now, is we're going to use these rules to be able to essentially take what we have and break it down into what we want. So two statements, A and B, are going to be said to be equivalent if the A, I'm terrible at drawing the little bold arrow, but essentially that, tautology biconditional, if you will, is always true. And if two things are equivalent, we're going to be able to essentially replace one with the other. So if I say that A is equivalent to B, then anywhere I see an A, I could write a B and it's the same thing. So we have a couple equivalence rules. Now don't completely panic. On exams, and I guess quizzes too, on exams you will have a list of the equivalence and inference that we're about to get to in a second. Rules. So no, you don't have to memorize them. You will know how you'll need to know how to use them, obviously, but you won't need to memorize them. You'll have them. So here's the names for these guys. So we have that P is equivalent to not P. That's not a typo. And this is called double negation. We have that P implies Q is equivalent to not P or Q. This is called implication. We have two cases of the next one. If you have not P or Q, it's equivalent to not P and not Q. It's kind of like the not distributes itself, but then the sign in the middle flips. Whereas if you have not P and Q, that is equal to not P or not Q. Again, the not essentially distributes. It's not really what's happening, but you can think of it that way if it helps. And the sign in the middle flip-flops. This is called De Morgan's laws. The next two are essentially just that you can flip-flop things in ors and ands. Saying P and Q is equivalent to saying Q and P. Likewise for or. This is commutativity. The next one is essentially if you have a string of things with ands or a string of things with ors, they all have to be the same symbol. You can group them essentially in any way you want. So if you had P and then in parentheses Q and R, it would be the same thing as taking in parentheses Q and R, P and Q and then R. So you can kind of move the parentheses as long as, now just for and or, okay? It's not just that the symbols match, it's just that it's for just and or. Saying that is weird. And this is associativity. And this last one is called distributive property. And these last three sound very similar to things you have in, arithmetic. So here essentially what's happening is you're distributing the thing in the front. So if you start with a P and, that, oh my lord. Nope, wrong spot. That P and, excuse me, is going to go to both things that were originally in the parentheses, and then that and is going to go in between. So it kind of takes that P and takes it to each one separately, and whatever was in the middle here is going to stay in the middle of the result. So that's the thing. It kind of works exactly how distributing a number through parentheses works. So those are equivalence rules. Now with equivalence rules, you can go either way. So if you have P, you can rewrite it as not P, or if you started with not P, you could rewrite it as P. These go in both directions. They're equivalent to each other. So, whoa, can you not do that? Why are you doing that? Lord Almighty.
So let's see if we have a statement. If you are not shorter than 48 inches and you are not pregnant, then you can ride the roller coaster. So say I wanted to split these up into their little pieces. So I'm going to go ahead and name this piece right here. Now, since it has a knot in it, I'm going to make it not P. And this piece here, since it has a knot in it, I'm going to name this not Q. And then ride the roller coaster, it's going to be R. Let me just write those out really quick. So our P value, since the thing that's in the statement is not P, that would make the P UR shorter than 48 inches. Excuse you. And the not P is the actual statement that's here. You are not shorter than 48 inches. Again, since the thing I have written down was technically, I forgot that people need to hear me. Since the thing that I have noted is not Q, then Q in general is going to be you are pregnant. Pregnant. And then not Q is, of course, you are not pregnant. And then R is you can ride the roller coaster. So just kind of putting out, in generality, things we kind of already knew. So that means that I could rewrite that entire thing up there as not P and not Q. And those are grouped together because they're all within the if statement, implies R. So that's essentially the thing I have right here is not P and not Q implies R. So say I let A be the statement you are shorter than 48 inches and you are not pregnant, essentially this piece right here. Okay? So just write it out again, because apparently I left myself space to do that. And then let's let B be the statement. It is not the case that you are shorter than 48 inches or pregnant. Now this is not the case that all of that thing that I just said. So it's not the case that I'm shorter than 48 inches or pregnant. Okay. So note that the B statement that I just wrote down is equivalent to A, specifically by De Morgan's law. And I really wish there was a way that I could keep the rules, up here while I'm still scrolling, but I can't. I guess I could write them on the board, but that doesn't help the Teams people either. So just trust and believe, I guess. It's equal to De Morgan's law. And therefore, we can substitute it. So essentially, if I wanted to say this statement right here that I originally had, I could also write down not P or Q implies R. And these two things mean exactly the same thing. Okay, so it's just a really long-winded way to say that these rules are going to allow us to say the exact same statement, just in a slightly different way. Yeah?
This is sort of similar to like feedback or something. You have two similar symbols, feedback and outside of the views.
So team, someone just asked, is this similar to factoring out a common number? So I know I said that the distributing is somewhat like that, and maybe I should have not said that because I want to be careful. Because it's not just that we can pull it out, because also that symbol in the middle has to flip. So yes, with quotes around it, team people. But I also, I'm very scared of saying yes, because someone could definitely abuse that wordage and say, well, you said it was like factoring. Well, no, it's slightly different than factoring because there's an extra piece that you need to keep track of. But it's a similar wishy-washy feel, but not exactly the same. Okay, let me erase some of this hoopla. So moving on. I said I have to stop talking at 2:15. Okay, good. Okay, do more stuff. So those were equivalence rules, okay? Now we have different types of rules, and then hopefully, I don't know if today we'll get to it, but at some time we'll actually see how these are actually going to work. So an inference rule is used when you know a stronger statement. So a stronger statement A and can conclude a weaker statement B. So essentially you know something that's stronger than the thing you really need, so you can kind of say, well, if I have that, then I know this weaker condition as well. So for example, let's say Julie pays no sales tax, and if Julie lives in South Carolina, she suddenly turns to Julia. Sorry, Julie pays sales tax. So essentially, so Julie pays no sales tax, and if she lives in South Carolina, then she pays sales tax. So that's the stronger statement. But if you kind of think about what that is implying, you could also say, okay, well then Julie does not live in South Carolina because she pays sales tax, but if she lived in South Carolina, if she paid no sales tax, then she'd live in South Carolina. So she does not live in South Carolina is actually, though, a weaker statement than the original. And here's why. If A is true, then B must be true. So essentially, if A is true, if Julie pays no sales tax, then Julie does not live in South Carolina, because we're told that if she does pay, if she doesn't, I've written that wrong. She pays sales tax. There we go. Sorry, we're told that Julie pays sales tax, but if we were also told if she did not pay sales tax, then she would live in South Carolina. So since she does pay sales tax, she must not live in South Carolina. Sorry, I messed that up in my brain. Does that make sense? I always want to triple check whenever I mess up like that. Okay. So, but now what if B is true? Does that mean that A is going to follow immediately after? Well, if B is true, that means that Julie does not live in South Carolina. But that doesn't tell us anything about whether or not she pays sales tax. So we know she lives in, so she could live, excuse you. So she,
I don't think that's it.
Hmm? The one that I wrote?
Yeah, because it says if Julie lives in South Carolina, Julie pays sales tax. And you have it if Julie pays.
Oh, Jesus, I'm reading it again. I'm reading it wrong again. So what I had here was fine. Hey, how we doing? Are we ready for class? All right, cool. Teams people are very confused. Okay, let me take a step back and do this again. Julie pays no sales tax. And if Julie lives in South Carolina, Julie pays sales tax. Okay, I was grouping them together wrong in my brain. So she doesn't pay sales tax, and that means she doesn't live in South Carolina, because if she did, she would pay sales tax. Thank you. So if A is true, then B must be true. Well, Julie pays no sales tax, then Julie does not live in South Carolina, because again, what I just said, if she did, she would. So yes, what I wrote down first was the correct way to view it. So for A, someone in chat is saying, so let's say, well, if you wanted to change it into symbols, we would have something like, let's say, so person in chat, let's say pays sales tax is P, and let's say lives in South Carolina is Q. And those are actually the only two statements we're worried about here. So why do I have these weird things popping up? Okay. So we don't need an R here. So here, if we were saying Julie pays no sales tax, so that would be not P. And Julie lives in South Carolina, so Q. Julie pays sales tax. Sorry. And if Julie lives in South Carolina, probably also the problem is there should be a then there. Then Julie's pays sales tax. So if she lives in South Carolina, she pays sales tax. So this is what that would be in symbols. So we need to kind of keep that implication together. It's if she lives in South Carolina, then she pays sales tax. Okay, cool. Okay, sorry about that. Sorry. So if B is true, does A follow? So Julie does not live in South Carolina. But again, we don't know whether or not she pays sales tax. She pays sales tax. So she could live in Georgia, but pay sales tax. So just saying she does not live in South Carolina, we can't imply anything about whether or not she pays sales tax. So that means that B is weaker than A, okay? Whew. So inference rules are essentially when we have the stronger statement that we can then pull a weaker statement from. These only go one direction, as opposed to the equivalence rules where you can go both ways. This way you can only go one way, which we just saw that I completely butchered. So, and now these are, the first three are written in that kind of new notation that we have, right? So remember, this is saying that if we have P and we have Q, and the second one would be saying if we have P and we have P implies Q. So remember, it's kind of like an and that's linking those two things together. But if we have P and Q, then we can imply P and Q, which is going to be called conjunction. And remember that this boldness is talking about a tautology. Whatever is on the left is taken to be true. I don't think I've said that yet, and that's important. So we're taking P and Q to be true whenever we're writing it like this, okay? Specifically when you see that type of notation, it's taking whatever is on the left to be true. So if you think about it, if P is true and Q is true, then you can say that P and Q is true. That's why we can do that. So if we have P and we have that P implies Q is true, we can imply that Q is true. Because if P implies Q is true, and we know that the original, if P implies Q is true, and we know that P is true, it must have been the case that Q is true. Like, that's the only way that can happen, right? You can't have true implies false. So that's why this works. And this is called modus ponens. So I did say we'd see that eventually. Modus ponens. So if we have not Q is true and P implies Q is true, then we can imply not P in a kind of similar way. You can talk yourself through it as I just did here. This is called modus tollens. And then if we have P and Q, we can always say P, that's going to be called simplification. You can also take Q out of it. It's not specifically that you can take just P, because if P and Q is true, then P must have been true, or Q, whichever one you want to take. And then if you have P, you can always change it to P or Q, because if P is true, P or Q is going to be true no matter what or is, no matter what Q is. Good Lord. So this is called addition. So again, you will have these, so the left side of these are true. Yeah, so that's essentially, remember what these bold arrows are saying, that we're implying a tautology. So we're saying that the left is true, which also means that the right is going to be true because it's a tautology. So 15 minutes. So let's see an example. So on Tuesday, then, we'll go through a few more proof examples, but I want to at least present to you one proof. Now I'm going to kind of walk us through this one and kind of trust and believe me for a little bit. And then on Tuesday, we'll definitely get into a bit more. So a proof sequence. Woo, ran out of space. A proof sequence is a sequence of statements and reasons to justify an assertion of the form A always implies, I'm going to start saying maybe C. So say we wanted to use a proof sequence to prove if we have P or Q and we have not P, then we can imply Q. And here's how these are going to go. We're essentially going to set up a 2-column table. We're going to have the statements, and we're going to have the reasons. Now, the first thing you always start with are your givens. And the givens are anything that's on that left side, all the things that you are assuming are true. Okay, so we're assuming that P or Q is true, and we're also going to number these because we're going to want to refer back to them. And I'm also given, whoops, I'm going to number them, so I need to number them uniquely. And I'm also given not P. Okay, and in the reasons column for those, you're just going to write given, because that's why you can write it down, because they're given to you. So now I want to somehow use all of those rules that we just talked about, either set of them. It's not like I can just use one or the other. And I want to try to somehow get down to Q. Now, again, I'll talk about this in much more detail on Tuesday, but it's almost better to work backwards for this one. But I'm just going to lead us forward. So what I'm going to do is the first thing I'm going to do is I'm going to use that double negation rule. So I'm going to take this first statement. So I'm going to use, double negation. And the thing you always want to also label, and this is why we label them with numbers, is you want to tell us which one you're using that rule on. So I'm taking that first statement and I'm going to use double negation on it to get not P or Q. I took the not P and I double negated it. I don't have to double negate both of them. I can double negate whichever one I want. And again, you might not see where I'm going with this. Again, it's better to work backwards from this one, but just trust and believe me for this moment in time. What we can do then is we can take the implication rule. And this one's harder to remember. I think the double negation kind of just makes sense. Let me remind us what the implication rule says. So the implication rule was the one that says P implies Q is equivalent to not P or Q. So I'm essentially taking not P and Q. Now I know I have that extra not, but that's because that's going to leave me with not P implies Q. But that's okay, because I just took the piece that was equal to and rewrote that and left whatever else I had. And now we're almost done, because notice that I have not P implies Q, and I have not P. Okay? I have not P implies Q, and I have not P. If I changed this to not P and not P, which again is still perfectly okay, these can be changed to nots in any way and they still hold. Yeah? Yeah. So I was pretty much done at that point anyway. So if I not that modus ponens rule, I can then use it. So for my last and final statement, I can use modus ponens on 2 and 4 to just be left with Q. That last one lost me a little. Yeah. So let me give people a second to write that rest of it down. And I do have a couple more minutes to try to explain that a bit better. The other thing that's unfortunate, just like with the precedence rules in the very beginning, is that this takes just a lot of practice to get good at. It's unfortunate, but it's what it is. And sometimes the easier way is to actually look at what you need and try to work backwards. So say, oh, I need Q, and kind of look at what you have and see, well, if I could make it this, then I could get there, and see if you can make what you need. Yeah.
Or could you just like look and see, like, so with an OR statement, only one of them has to be true, and you can already see that not P is true, so you know P is false. So you can already assume from there that Q is true.
When you're talking to someone on the street, yeah. what we're trying to do here is give you indisputable proof that it works. And also, this one's quote unquote simple, and I don't want to say simple and make you feel bad if you were lost at it at all. Like, I'm not trying to say that at all. This is hard. But this is a more quote unquote simple example. Once we get to the more in-depth ones, you're not going to be able to talk yourself through that. So yes, technically you could kind of reason it out, but what we're really looking for is this firm proof that it works. So let me try to explain this modus ponens one again, because I got a couple minutes. So these first, well, let me just start and just do the whole thing over again too. So these two were given. So those just get written down just because we have them. And if you want, you can like space down a little bit and put what you need. Now, you don't know how far you're going to need to space out, so you might have to erase it and move it down later. But you can also kind of remind yourself what you're trying to get to. Okay, and you need to try to figure out the rules that you can use with these two things that you're given to get what you want. So if I'm looking at this and I say, well, I have P and Q and not P, and I'm looking at my list of rules and I'm like, none of these are helpful right off the bat, so I've got to try to find something that will give me Q. The first thing I would do if I was working backwards is I would start looking at rules that give me Q. So I would start, and again, I'm sorry, I can't pull up the, well, I guess I can scroll up and talk about the thing I'm about to look at. So say, now we don't have the implication rules in front of our face. So say I'm looking at this one and I'm saying, okay, well, I want to try to get to Q. And I'm like, okay, well, this one gives me Q. So that might be a decent place to at least try to start looking. It might not be right. You might not actually need it, but it's a good place to start. So that tells me that I would need P or, sorry, implies Q and P. Well, I don't have either of those, right? I don't have either of those at all. But I have not P. So I also know that if I could find somehow not P, I've just forgotten, sorry, implies Q. If I could find this somehow, I could still use modus ponens because I have not P in there. Well, is there a way that I can find that? Well, if I changed this and I'm looking at my rules and I say, okay, well, this implication rule gets me a not P, but I don't have that. Like, I don't have the not P to use, if that makes any sense. So, well, I can get myself some knots by just throwing in some double negations. So let me just toss in some double negations. I'll have too many knots, but that's okay, and I'll try to see what I can work with. I know this is sounds very wishy-washy, but this is how I would think through it, and I know people can probably think of better ways to think through it, but that's what I would do. And you kind of are like trying to take what you have, take the rules that you can use, and try to figure out how you can piece them together. So in this case, the first thing we did was we double negated the P from the first statement. So we threw two knots on it. And then I realized that if I take just this piece, I could kind of get what I possibly wanted of this not P implies Q by doing implication. And then from that, and let me try to say this one out nicely. So modus ponens tells me that I need P implies Q, and that will get me Q. Now you can manipulate these with knots as much as you want. Like putting a knot on there doesn't, as long as you are consistent, will not change the rule. So if I change this to not P, I'd have to change this to not P, but the rule still stands. Okay? So then I say, okay, well, I have not P, and I have not P implies Q, which is exactly this kind of tweaked format of modus ponens. So I can use modus ponens on those two lines to get me Q, exactly what I wanted. Okay? So yes, I know that these proof techniques are, they just take time and practice. And on Tuesday, we'll go through a couple more examples. And the one example we're going to walk through very much does that backwards thinking. Like you get to a part where you're like, I have no idea how I can get from what I have to what I need. Let me see what I need and try to work backwards to what I have. Okay, so you can always try to go like backwards and forwards, however much you need. So we'll talk about this more on Tuesday. At this point, it's time to take our quiz. So I'm going to stop the recording. Oh, there was, so I don't know. Yeah, so the implication rule is telling us that we can take that not P or a Q and change it into an implication. I'm going to stop the recording.